Good morning or good afternoon, ladies and gentlemen, depending on where in the world you are. I would like to welcome you internationally. We have a truly international audience again today to our second webinar in the HEKA Electrophysiology update series. My name is Jan Dolzer. I'm the Vice President of Sales and Marketing here at HEKA Elektronik. What are we going to talk about today? So, for this introduction, I'd like to call that warm words for a welcome. I will talk about a few housekeeping items that help you getting along with this webinar a little better, and a few other organizational issues. I'll go into a brief product update. What's new? What's new since our last webinar, since our last user meeting at the Neuroscience Conference? Then the original plan was having Christian Heinemann talk about current clamp recordings with the EPC10 patch clamp amplifier. Unfortunately, Christian had to stay home with a family emergency. So his talk, as you may have seen from the loop that ran earlier, will have to be postponed. We are trying to record his talk and make it available offline together with the recording of this webinar. So we changed the order of the other talks. Telly Galiatsatos will talk about current clamp recordings with Patchmaster software. Originally, he was going to focus on software entirely, and Christian was going to cover the hardware aspects. Telly will take over some of the hardware-related aspects from Christian's talk, and have a little more time to go into the software. And then at the end, I will speak about intelligence in a two-electrode voltage clamp amplifier, the iTEV 90. And in the very end, we will have a question and answer session. You have the opportunity, I'll go to that in one or two slides in more detail. You will have the opportunity to type questions to the presenters, and we will address all questions either in the Q&A session at the end of this webinar or offline by email. If you do not get audio, well, then you don't hear me saying this now. Audio is transmitted over the IP connection right now. So you want to turn up the volume on your computer. And if you don't get volume or if you don't have speakers, pick up the phone and dial in at the number that is most convenient for you. If you have any questions, as I mentioned earlier, use the Q&A section in your session control panel that is on the right of your screen here. Indicate which speaker your question is directed to. For some questions, that's very easy for us to figure out, but for other questions, it's not quite that straightforward. And as I mentioned, all questions will be addressed either at the end of this webinar or we will get back to you offline by email. That means you also have a chance to ask questions that are unrelated to the actual talk. We will still get back to you about that. You also have the opportunity to do that in a short survey that we will direct you to after the webinar. We are asking you about what kind of research you're doing so we know where your feedback is coming from, but we also understand what your needs are. For example, it's interesting for us to know how many people do single channel recordings as opposed to wholesale, how many people do wholesale recordings from slices as opposed to dissociated cells, etc. You also have the opportunity, obviously, to ask us to get in touch with you about a support issue or if you need a quote or something. Or, most importantly, leave us suggestions for topics for future webinars or user meetings. The focus on current clamp today is based on feedback that we received from attendees of earlier webinars or user meetings. And of course, we realize your time is as valuable as everybody else's, so we did our best to keep the survey short. Documentation is available after the webinar. This webinar will be recorded, and the recording, together with the slide decks, will be available for download, well, shortly. With the holidays coming up, shortly may mean next year, will be available on the user meetings and webinars page or past events page on the HEKA website. So just navigate your way from HEKA over events to user meetings and webinars. The recordings are hosted on YouTube, or for our Chinese customers who can't access YouTube, on Youku as well. And the slide decks are available in PDF format. And if you need a slide for teaching purposes or something, on request, we can also share the original PowerPoint presentations. Talking about user meetings. If you did not have a chance to go to the neuroscience conference and or not have a chance to attend our user meeting in San Diego, that may be part of the reason why you're here today. You may still be able to download the presentations. They are fairly similar to what we're going to present today, but of course we learned off from the user meeting and have made appropriate changes. Our next user meeting will be at the Biophysical Society annual meeting in San Francisco on February 17th from 5:30 to 7 p.m. and that's going to be at the Moscone Center in San Francisco, California. The registration for that will open in mid-January. If you are on a mailing list, you will receive an invitation for that. To sign up, if you're not on the mailing list, to sign up for the notification emails, please send a message to events@heka.com. Now let me switch gear and go to the product update. What's new? Well, I'll briefly go into the imaging extension because that's not really new. We talked about that last time already. The imaging extension for Patchmaster and Patchmaster data acquisition software. Brief recap, what does it do for you? It allows you to synchronously record electrophysiology and imaging data. So you can generate concurrent time course plots in real time during the actual experiment. You also can access images or frames associated with an individual sweep with one click by just clicking on that sweep. And one of the simplest applications for this software is actually archiving an image of the recorded cell. So if you don't trust your grad student, well, you should always trust your grad student, of course. So if you want to monitor what type of cell was recorded from, just for archiving purposes, just for documentation purposes, you may want to keep an image of that recorded cell. Now, what's new here is the bundle that we newly offer of the imaging extension software and the Genoptic Progress MF camera. That's a camera that we know is compatible, have tested a lot with the imaging extension software. Compatibility is limited by the fact that the camera needs to support the so-called bulb trigger mode. That's the only way for the software to control the actual exposure time on and off and accurately time the point of time when the image was taken and synced it up with the electrophysiological recording. Also, what's new is Patchmaster. Version 2.73 was released a couple of months ago already with bug fixes and a number of new features. There were more new features in Patchmaster 2.71, which was released earlier in 2013. We are trying to release 2 to 3 public releases every year, and of major software packages like Patchmaster and Podmaster. It may be less for other software packages. They're all available on the HEKA downloads page, together with a few other useful things like manuals, like drivers, or also brochures. The HEKA downloads page, there's a link right on the HEKA homepage. So much about the product update. Now let me introduce the first speaker, Telly Galiatsatos. Telly graduated at Queens College in New York in computer science in '87 and then joined Instratech Corporation, initially in IT engineering support. Then he became a software engineer, took care of sales and support, became a product specialist for HEKA products, and finally the general manager. And since 2007, when Instratech merged with HEKA Electronics, he's been the general manager for HEKA Electronics in the US. The title of Telly's talk today is going to be Current Clamp Recordings with Patchmaster Software. With that, I'll hand over to Telly. And we'll unmute him.
Thank you, Jan.
Telly, you're on.
Okay. Sorry, I still didn't get the screen change
Okay,
notification.
let me see. Sometimes that dialog popped up in the background. Okay, now it should work.
Okay, does everybody see my PowerPoint presentation with the title Current Clamp Recordings with Patchmaster software?
Yes, we see that, and so I'm going on mute, and it's all yours.
Great, thank you very much. So, I like to basically my talk will be all about current clamp recordings with on the software side of it. I will briefly discuss a few of the hardware features, in particular with the EPC10 revision amplifier. So, talk today. Uh, First, we'll start off a little bit with the EPC10, in particular with the revision T hardware overview. Then we're going to go into a couple of examples of recordings. So we'll start off with intracellular recordings with high resistance electrodes, and we're going to do that by simulating it with a model cell. Then we'll go into current clamp recordings. We'll show the PGFs, or the pulse generator sequences, for a couple of different recording types. Then we will go into voltage clamp recordings, in this case using an extra potential that was recorded previously as a stimulus. And then finally, we're going to go into some examples of using the online analysis, in particular the action potential functions that we have built in. So let's get started. So here we have just a quick schematic of the current clamp circuitry, the feedback loop that's available with the EPC10. What can we measure with current clamp mode? We measure the membrane resting potential, spontaneous action potentials, elicited action potentials, just to name a few. Let's go a little bit into the extended features of the EPC10, and in particular the revision T, which has been available for, I guess, a little bit over a year now. So we have an increase in the voltage stimulus range. Previously was plus or minus 1 volt. Now we have doubled that, so it's plus or minus 2 volt. To enable these features, we have added a control in the EPC10 pull-down menu in Patchmaster to do so, and it's right here. Now, for current clamp recordings, we have following new possibilities. We now have increased the voltage measuring range to plus or minus 5 volts, and an increase in the current injection by a factor of 5. Also included with all EPC10s is the what we call the Red Star head stage, which features a lower noise performance. So as you can see here, it's 31 femtoamps at 1 kilohertz. Now, all of these hardware controls are handled through the Patchmaster software, and actually from the amplifier control window. And I'll go over some of the controls and how they vary when you switch to current clamp mode. I will start off with some of the controls like the gain, the mode setting, the compensation, C fast, C slow, the bridge adjustment or bridge compensation, the filters. We'll go a little bit into the external stimulus capabilities and some of the additional controls for when you switch to current clamp mode. Okay, let's get started with these additional controls. So one of them that is specific for current clamp is the so-called gentle switch option. And we have two possibilities. By default, it is switched on, but you can have it off, which means that when you switch from voltage clamp to current clamp, I-membrane will be set to 0 picoamps. But if it's turned on, then I-membrane will actually be set to a value that will keep the membrane voltage at the commanded voltage in voltage clamp. So for example, in this illustration, we started at minus 70 millivolts holding in voltage clamp, and it was converted to 138 picoamps when we switched to current clamp. And this is done automatically. Now, two other controls that interact with each other and actually influence some of the other controls in the hardware are the current clamp gain and the current gain. So for current clamp gain, we have up to 4 gain range settings that are available, and this basically allows us to set the maximum current injection. And this control is available from the Show All tab in the EPC10 control window, and this control needs to be set before you switch to current clamp mode. Once you switch to current clamp mode, this control is actually disabled. Now, based on what the gain range or the CC gain is specified, then you enable which feedback resistor is used in the head stage. So which gain settings for current gain, or in this case our stimulus gain, will be used. So if we have a gain range of 0.1 or 1 picoamp per millivolt, then we are working in the medium gain range. Then the following gain settings are available. Or if we go to a gain range of 10 or 100 picoamps, then we are working the lower gain range, and then these current gain controls, or these current gain scaling factors will become available. Voltage monitoring gain. So the EPC10 allows us to amplify the voltage signal either by a factor of 10 or 100 before it's digitized. Another feature, hardware feature of the EPC10 is the capability to use an external stimulus input for both. It's actually available for both voltage clamp or current clamp through BNCs on the front panel of the EPC10, and this option needs to be enabled. So if you're feeding in a signal through here, it will be added to the internal stimulus that is generated by the built-in digitizer. Now, to enable this option, depending on which version of the EPC10 you have, it's either a single or a multi-unit amplifier that controls in two slightly different places. For a single EPC10, so it is next to the Stim filter settings, and you just enable the external control. And for multi-unit EPC, what we call EPC10/N, in this case, a 2 amplifier version. It is in the control panel, but next to each of the amplifier. And each amplifier can be set individually. Now, keep in mind that the scaling factor for the stimulus input is scaled based again on what the value of our CC gain was set to. Filter 1. Now, in current clamp mode, filter 1 is actually not a user-specified item, but it will actually be handled by software, again, based on what the settings of our current injection are. So if we have a gain setting of 0.1 or 1 picoamp, then filter 1 will be automatically set to 10 kilohertz. Otherwise, it will be set to 30 kilohertz. Filter 2, and something that has changed in the last, actually right before revision T, is the capability to have filter 2 apply to various points in the hardware. So filter 2 can actually be routed or applied to the current signal, either with a Bessel or a Butterworth response. It could be completely bypassed, or it could be applied to the voltage signal, again, with either a Bessel or a Butterworth response. And this is something new, and this is in current clamp recordings. Since this is our response, we now have the capabilities to filter this signal. Another control that's in Patchmaster on the EPC10 that needs to be handled for current clamp is so-called bridge balance. What is bridge balance? So a balanced bridge is the ability to eject current through the resistance of the pipette while still measuring the true membrane voltage. When switching from voltage clamp to current clamp mode, the control in the EPC10 window, RS comp, will be transformed to bridge, and it's initially set in the off position. Now, there are two settings that handle the bridge and that we need to take care of, and one is the time constant, and then what values are available as a time constant would depend on what the CC gain range setting is specified as. And then the percentage control, which is the percentage of the series resistance used for compensation. Typically, we start off at 100% and then adjust accordingly. Now, with the bridge compensation, the following axis resistance, the maximum axis resistance that can be compensated, again, it has to do with our CC gain range. So from 0.1 picoamps to 1 picoamp, we go up to 500 megohms. Otherwise, 10 to 100, it is 5 megohms. Now, C-fast compensation. So both C-fast and C-slow compensation are actually handled in voltage clamp mode before we switch to current clamp mode. So typically in voltage clamp mode, we're going to perform an auto C-fast. This will neutralize the capacitance of the electrode. When we switch to current clamp mode, the automatic C-fast compensation will be disabled, but the values are still available. And then C-fast will be reduced by 0.5 picofarads, to reduce the possibility of oscillation, which could potentially lead to the destruction of the cell membrane. C-slow compensation. Like I mentioned before, again, we perform an auto C-slow in voltage clamp mode. This will cancel any remaining capacitive transients, and it will get initial estimates of membrane capacitance and series resistance, and this is very important. So when we switch modes, we start in with a nice level base system. When you switch to current clamp mode, so C-slow compensation will be turned off. And why? Again, because C-slow affects cellular parameters, which in this case will distort our voltage signal. Now, recap of what happens when we actually change our recording mode to current clamp. So the input of the head stage will act as a high impedance voltage follower. The feedback resistor will be used for stimulation. Again, depending on what our CC gain setting is set, it will be either the 500 megohm or the 5.1 megohm feedback resistor in the head stage. On membrane will be set, again, based on the value of the gentle switch control. Internal stimulation, or our test pulse, will be turned off. Filter 1 will be set to either Bessel 10 kilohertz or 30 kilohertz. C-slow will be turned off. C-fast will be reduced by 0.5 picofarads, as I specified earlier. And finally, the RS compensation control will become bridge balance. Okay, now that we have our hardware ready, prepped to go, we're going to give a few examples on PGF, on sequences for acquisition. So first we'll go into high resistance electrodes. And this we're going to simulate using a modified model cell. It's slightly different than the model cell that is included with the EPC10, but basically the same concept where we have 3 different switch positions that will give us that will emulate different portions of the cell. So the top switch position, we have high resistance of 50 megohms, which simulates a pipette in the bath. Then we have the middle position, which is a clogged electrode or an ideal on-cell configuration, just a capacitor. And then finally the lower position, which will simulate an impaled cell with a high axis resistance. So let's put the model cell in the upper position, which will simulate the electrode in the bath. When we select our amplifier window, a test pulse will be sent out based on the parameters we specify here. Current and the voltage are acquired. Here is our voltage, in this case our stimulus, and our current monitor. We press the setup button, which actually executes a protocol which resets the APC10 amplifier and also performs an auto V0. And as you can see here, it adjusts for any offsets that we may have. And finally, calculation of the membrane resistance, which based on our model cells, approximately 50 megohms as shown on this control here. Now, we move the model cell to the middle position to simulate a gigaseal. And here again, we have our response. We perform an auto C fast by pressing on the auto button under the C fast control. And here we have a capacitors neutralization. Now we go and we move the switch to the lower position, which will simulate impaling a cell, and perform an auto C slow to remove any of the transients from this circuit. Now, when we switch to current clamp mode, as I mentioned before, the test pulse is first disabled. So you see here we have no change as you from the gentle switch was turned on, so our membrane was changed to 138 picoamps. When we enable the test pulse, we now have, here is our voltage signal, which is now our response, and this is our stimulation, which is our current. And you could see if I blow up the voltage signal a little bit more that we have a misadjustment because the bridge is disabled. Now, we will enable the bridge by setting it to 100%. Oops, sorry. Let me go back. Set this to 100%. As you can see here, with this compensation, we have a pretty good signal. And the reason for this is because we started with good initial values. So this is why it's important to go and perform an auto C slow so we have good starting point or initial parameters for the system to get started with. Okay, so we're going to go into some of the current clamp recordings. Typical one is for action potentials. So I'll go briefly what an action potential is, things that we need to take care of. So we have, so here is actually an example, and we have our resting potential, stimulus or current injection that we'll be using to elicit this action potential. A threshold where this is where we need to be greater than to get this to fire. And we have here our depolarization phase, our repolarization phase, and finally the refractory period, which goes back into over waiting period for the resting potential. Okay, so we'll go over a couple of PGF sequences that we could use for current clamp recordings. So one example of this is to perform a sequence to record some action potentials, which we require 3 segments, being our baseline, our stimulus, and then our waiting period. And we have this sequence as current clamp only. And we have here our template showing our current injection. So if we execute this, we recorded both the current trace and the voltage trace, and this is our results. Now, another PGF sequence that can be used is to record an action potential train. Here, big difference is that we are not we're keeping the current at a steady, constant level for a long period of time, hoping to get some action potential trains initiated. So here, we start off with our baseline, and then we go up to 100 picoamps current, and we just stay there for a longer period of time. So when we execute this, again, you can see here is our stimulation, our current, and here is our voltage response. Now, another sequence that we could create is to elicit action potentials or by triggering. Here we have many segments that we use to do this, to generate these triggers. And what's different about this one over some others, of the other examples that I showed, is that we now introduce parameters. Yeah, blow that up a little bit more. So instead of actually locking in numbers, we actually have parameters that we can change either from the pulse generator itself or through the protocol editor. So we can modify this sequence without actually going in and editing each segment. So if we execute that, this is an example of what we could see. This was acquired using our standard model cell. Now, another application is to actually take an action potential that we recorded and use that as a stimulus in voltage clamp mode. So to do that, we first have to export this voltage trace. So to do that, we go to the replay window, to our tree, to our data tree. We select the trace from our data tree. In this case, it's our voltage monitor trace. Once we have that selected, we go to the replay pull-down menu. We go down to export trace, and then we specify that we're exporting this as a stimulus template file. And we just enter a file name. And usually the file name has to be associated with the PGF that's executing this file template. So for example, if our PGF sequence was called CC inject, this would be CC inject _1 for channel number 1. So to execute this file template, we need a PGF sequence. The easiest way to do that is to actually copy one of the PGF sequences that we used before. Usually the best one to do is the one that was used to actually acquire the action potential initially. To do that, we select the copy command. We then enter a new entry name for this copy command. In this case, we'll just use AP template. And then we need to make a few minor adjustments to it so we could execute this. So first, we need to specify that for our D-Day output that we're going to be using a file template instead of data that's computed by Patchmaster. And we do that by selecting load from file template. We also need to change the type from current clamp to voltage clamp because this sequence will be executed in voltage clamp mode. And that should be it. And when we execute this, we now will get, so this is now reversed. So we now have, this is our current response, and this is our stimulation, which was our action potential from the file template. Current and stimulus. Okay. Now I'd like to go into a little bit of the online analysis possibilities in Patchmaster. So in Patchmaster, we added these action potential functions or action potential analysis as part of the online function types, as you could see in this illustration here. Now, these analyses are designed for evoked action potentials. So some of the different parameters that are available are baseline or resting potential, the amplitude of the action potential, repolarization amplitude, upslope, downslope. Same, we now have also parameters in regards to time. For example, time to maximum, time to minimum, so forth. All of these functions are explained in detail in the Patchmaster manual. And for these analysis functions to work, there has to be some criteria that has to be met. So the acquisition must contain a sweep of at least 3 segments, as I mentioned earlier, the baseline segment, the stimulus segment, and finally the weighting segment. The stimulus segment has to be marked as the relevant X and Y. This is exactly the same as we would do with voltage clamp recordings. We are telling the online analysis where to get these parameters from. Again, in this case, from the stimulus segment. And now a slight change in the way the cursors work with these functions. So the start of the second segment, or the relevant segment 2, is at the beginning of the second segment, the same as it would be in voltage clamp. But the difference, the end cursor is now the end of the third segment, with the end of the waiting period, instead of being at the end of segment number 2 as it would be in voltage clamp. Now, so here I will illustrate an example on how we set it up. So first we need to define our analysis functions, both X and Y. So for example, let's start off with our X function. We're going to specify a measurement. It's going to be maximum, so we're going to be getting the maximum of the current. We are getting this from trace number 1. This is our our current trace, our stimulation in this case. For our Y function, we're going to use an AP analysis function, and we're going to use action potential amplitude, or maximum. And again, we need to specify where this parameter is coming from. So in this case, it's going to be trace number 2, our voltage trace. Once we have our analysis functions defined, now we need to create our graph. So we first have to go in, we have to activate the graph that we want to plot. We want to specify what our X and what our Y values are. Then we need to specify the scaling, the axis scaling for this. And in this case, it'll be done automatically after each sweep. And since the data set that I'm using is actually is multiple series, I will enable the overlay button so that way the window is not cleared between each sweep. Finally, we need to specify what graph position or what window Patchmaster offers 2 online analysis windows for the results. And you could have up to 12 graphs in window number 1 and 12 in window number 2. We will specify window number 1, graph position number 1. So when we execute our data, either by doing it online, or in this case, it was after the fact by replaying back data from our data tree. You see here is our current, our stimulation. Here is our response. And here we have our online analysis results. And one thing you notice from here is that for the first 8 attempts, we had a sub-threshold depolarization, so we actually never got an action potential to fire until the final attempt, and here we have a nice classical action potential shape. Okay, another online analysis function which doesn't exist in Patchmaster, but can be created using the math functions, is so-called action potential duration at 80%. And it could be 80, 70, 90%. That is a setting that is available to you. So here we have, back to our example, we have our 80% rise time and then 80% decay. It's shown here with the yellow traces. And to get this function, we need to do a math function. We need to subtract the time from A to B. Okay, so now we need to create this using the online analysis. So first we go in and we specify our A function, which is going to be, again, from AP analysis. We're going to specify rise time delay. And with this function, we now introduce another control in the analysis function window, which allows us to specify the percentage, in this case 80%. And we also specify, again, what trace this parameter is coming from. We do we repeat this for our B value. So again, now it's another AP analysis function. This time we're going to use decay time delay. Again, specify 80% and trace number 2. So now we have A and B, and now we need to specify the math to do this. So we go back to our functions under the math category, and we specify A minus B. One thing I didn't mention earlier was in the analysis functions, you have the name is automatically selected, but you have the capability to edit it and change it to whatever you like. In this case, I'll make it APD80. So now in our analysis functions, we have this function called APD80. And now since it's a math function, we need to define what is A and B. In this case, we have the A, this case, which is index number 11, which is our delay time. And then we have our B, which is our rise time, which is index number 10. And you notice here that the trace is not activated since these parameters are coming from other functions. Okay, so again, we created our functions. Now we have to create our graph. Same thing, we specify X and Y value. This time I went and I selected graph number 2, so I'm going to make this a separate graph in our window. So I'm going to specify an online index, which will give me a sweep index as our Y, and then our ADP 80 time. Sorry, that should be APD 80. That's a mistake on my part. Okay, we need to specify the axes again. Again, we'll use the auto scaling feature and overlay, so to show it on the graph. And then finally, we're going to add a new graph position. So this is a new graph. So we're going to go and use the same window, except we're going to specify position number 2. So when we execute this, same data set as we had before, except now we have 2 online displays, 2 online graphs that are generated. So a little summary of my talk. So what's important in current clamp recordings is proper C-fast and C-slow compensation before switching to current clamp mode. This defines some nice initial parameters, so the system is in a stable state. When adjusting the bridge balance, we start with initial value of 100% and then adjust accordingly. To initiate an action potential, the current injection stimulus must be above the threshold. And finally, Patchmaster offers a variety of online analysis functions, including math and equations, user-defined equations. One thing I also would like to talk about with math and defined equations, these are not exclusive to current clamp recordings. These could be used for any recordings that you like to do in Patchmaster. And with that, I'd like to say thank you and pass it over to Jan.
Thank you very much, Telly, for this very exhaustive tutorial talk. Let me reiterate for the audience that the Q&A section is open in your control panel on the right. We have a few questions already coming in. I expect a few more. We will, as we mentioned, we will address them at the end of the webinar. Everything will be recorded, and at the end of the webinar, we will address most of the questions, and those that do not get addressed during the actual webinar will be addressed offline by email later on. My talk is a brief feature of one of our newer products, the iTEV 90 Amplifier, introducing intelligence to two-electrode voltage clamp. Briefly introducing myself, my name is Jan Dolzer. There seems to be a delay in updating my slide. I see that on my control monitor, so now you should see what I have. I graduated in Marburg in Germany, as you can hear from my somewhat weird accent probably, with electrophysiology in insect sensilla, or factory sensilla actually, and joined Axon Instruments in 2003, stayed there through several mergers, left what was left of Molecular Devices then in 2011, early 2011 to join Sutter Instrument, and as the product manager for laser-based micropipette pullers. In late 2012, I went back to electrophysiology to join HEKA Electronik and as the Vice President of Sales and Marketing. The agenda of my talk today, I'll give you a brief overview over the iTEV 90. I'll talk about the scientific background of two-electrode voltage clamp and highlight the benefit of computer control of computer-controlled amplifier. I'll go into a quick feature highlight, a couple features of the iTEV 90 and two use case scenarios. What can it be used for? Now for the overview, the iTEV 90 iTEV stands for Intelligent Two-Electrode Voltage Clamp Amplifier. It's a fully computer-controlled 2 or 3, that's why multi-electrode clamp amplifier. Now, what does it do for you? Of course, two-electrode voltage, but also current clamp. We just heard about current clamp. You can record from tissue slices, oocytes obviously, and also other large cells. The amplifier is fully computer controlled, and there's a lot of automation going on for easy amplifier setup. What else does it do? It has an integrated digitizer with a USB interface, so easy connection. It's fully supported by Patchmaster software. That means Patchmaster software controls all amplifier functions as well as the recording. And you have an optional third head stage for ultimate clamp speed and accuracy. But it also helps you to keep the recording alive longer. And there's a couple specialized applications where the optional third head stage is of benefit. A quick word on scientific background of two-electrode voltage clamp, the principles. In contrast to patch clamp recordings, you have two electrodes. You have the voltage electrode and the current electrode. Both impale the cell. They are not just in touch with the membrane, they impale the cell. It's sharper, higher resistance electrodes. You have a reference and a ground electrode. So the current passing electrode typically impales deeper into the cell to allow more current passing to the center of the cell. Then this is driven by an amplifier that in the end monitors the current that needs to be injected here, that allows you to measure the current through the cell membrane. And it gets a little more complicated with the third electrode, with the circuitry of the third electrode. The signal that comes out of this is then routed through a data acquisition interface, and the entire amplifier and also the data acquisition are controlled by a software user interface. All that does not need to bother us in too much detail, because what we as the users see is essentially the iTEV 90, the device, and then the software user interface. Now, what's the benefits of full computer control? To explain that, let me step back a little and look at what is the flow of information in electrophysiological recording. You usually have, in the old style paradigm, you have an amplifier, and the amplifier puts out an analog signal that gets digitized in the digitizer, converted to digital information, and then there's a piece of software that makes sense of the entire information, but at the same time, which is not shown here, the software also controls the amplifier and may put out stimuli, so a stimulus signal. With the iTEV 90, similar to what we did with the EPC10 patch clamp amplifier, we combined the amplifier and the interface into a single housing to make it more integrated. So the digital conversion is all in one step, and Patchmaster software controls all amplifier functions. There's no knobs and buttons on the front panel here. At the same time, that allows you to record all amplifier settings. Now, that's the benefits of the computer control. One is you can automatically compensate the offset, pipette offset, but also the measurement of the electrode resistances can be automated. The logging of all amplifier parameters and all measurements that are done by the amplifier. And you can save and recall clamp parameters for frequently used preparations. So you don't have to do all the setup again all over, but you just call your, well, this is my typical Xenopus program or something like that. You call a protocol file in Patchmaster, and then all settings are made like they were the last time. We talked about amplifier control by the software. This is what the amplifier control window looks like, the usual test pulse section. Then you can do voltage and current clamp, filter settings, and the potential in the potential electrode and the clamp controller. This is the tuning view as used from Patchmaster. We have three different views. We also have a monitoring view in which there's a lot less to see, and a show all view in which you have full control over all the less frequently used settings. Quick feature highlight. Nice feature is the hardware leak subtraction. If you are patch clampers, which I believe most of you are, you're familiar with P-over and leak subtraction. For those who are not, it's quickly shown here at the example of P/2 leak subtraction. You have two sub-sweeps, typically opposite polarity, and then a main sweep. And the responses to the current to the sub-sweeps are subtracted from the main sweep, and then that would cancel out any capacitive transients and also leaks that are passive ohmic resistances. In the iTEV 90, there's a hardware leak subtraction, so this algorithm is not software-based. The advantage of that is you can set a higher gain, since the capacitive transients do not drive the amplifier into saturation, which they would do in software. So in software, you would have to reduce the gain to avoid driving the amplifier into saturation, because then it wouldn't recover quickly enough if it comes back from saturation. You also have we also have the potential for doing better temporal performance by implementing predictive compensation. That means you wouldn't execute the sub sweeps in every main sweep, but only every, say, 10 or something like that. But we need to probe whether there's enough demand from customers to make it worth our while to implement this feature. So it's up to you to ask that. The third electrode, what does that do for us? Compensation of extracellular field potentials to remove inhomogeneities in the voltage clamp across the membrane. With the largest cell, you may have inhomogeneities. If you bring the third electrode in close vicinity of the cell, that may make the clamp more homogeneous. And also you can use the third electrode as a second current injection electrode. Both these electrodes are impaled into the cell, and that means you can pass 2 times more current for very large cells. And again, that leads to more homogeneous voltage clamp. A quick use case scenario, just to show that it actually does what it does. Voltage clamp recordings of a sodium channel and a potassium channel, the EAG channel in this case. Those were courtesy of Stefan Heinemann from the University of Jena in Germany. Another use case scenario is measuring membrane parameters. In this paradigm, the resistance is determined from the current response to voltage step, and the membrane capacitance is determined from the current response to a voltage ramp, up and down ramp. And again, this can be automatically computed and logged through the Patchmaster protocol. So let me summarize. When is two-electrode voltage clamp the right choice to begin with? Whenever you record from large cells like xenopus oocytes, which many people still use because it's easy to express ion channels in them and they have low background currents. In general, when you have large currents, it may be a method of choice, and that is also the case in certain tissue slice preparations, and I'm sure this list could be continued. When is it not the right choice? Well, if you have small cells, like in most expression systems, and those of you who do patch clamp probably use those cells. When you have fragile cells that you cannot impale with pipettes, this is the case with most primary cultures, or also the majority of the tissue preparations, or when you have very small currents, and that includes, but is not limited to, single channel recordings. So the iTEV 90 fully computer-controlled multi-electrode clamp amplifier is the intelligent choice for two-electrode voltage clamp. With that, thank you very much for your attention to this talk, and let me bring up the Q&A panel again. Just a reminder, Q&A panel is on the GoToWebinar control panel, which by default is positioned on the right side of your screen. I see we had a few more questions come in, and let me unmute Lars, who will moderate the Q&A session. You're both on, Lars. I think you muted yourself.
I'm on.
Okay, Lars, can you hear us? Okay, I'm sorry, we cannot hear Lars. So let me see whether I can make sense of the questions that I can see here. Here's a question that goes to Telly, if I interpret that correctly. When doing whole cell patch clamp, when should we hit the C-slow and whole cell mode? Also, both of those should be done before going over to CC, question mark.
I'm sorry, I didn't quite understand
So
the question.
when is a good time? Lars, it seems like we have you on the audio now. We hear some background noise.
Okay.
Okay,
Thanks.
so but let me continue with this question, and then we'll go over to you, Lars. So Telly, when you do whole cell patch clamp, the question essentially is, when is a good time to do the C-slow and whole cell mode, the C-slow compensation, and go to whole cell mode? And the second part of the question is, should that be done before switching to from voltage clamp to current clamp?
Yes, it should be done before switching to current clamp because it gives you some initial parameters for the cell parameters. So when you switch, you now have a known good state. Otherwise, you have unknown values to start with. So it's always best to prepare your setup before you switch modes. In terms of when to do C-slow, I mean, typically, I would assume that you want to start compensating first for C-fast, making all the electrode capacitance transients neutralized before you do C-slow. That would be probably a good time.
Okay, thank you. With that, over to you, Lars.
So I have two kind of organizational answers. One of you was asking if he could download previous talks somehow. Yes, the current talk is being recorded, and previous talks have also been recorded and are available on our website, so you won't miss anything. Also, the questions that will not be addressed, we will collect them all, put them in a document, and later on you will also be able to download those from the website, including answers, of course, as well. So that'll take quite some time, so don't expect that to be done this year. Probably in January this will be done. Then one of you was proposing another topic and was asking if we could talk about. Yeah, we're happy to get your proposals for topics for the next webinars. I can't guarantee, of course, that we'll talk about those, but we're happy to get your proposals, and we'll definitely take them into account. So thanks a lot for that. So, Telly,
yes,
a question addressed to you. I mainly work on studying the action potential from stem cell-derived cardiomocytes when I try to pace the cells at fixed frequencies. So 0.5, 1, and 2 Hertz via recording pipette. I sometimes cannot capture it very well. how to get a better pacing by recording pipette.
I'm sorry, I don't quite understand the question. I mean, would you be able to send me some illustrations of what the problems are so we could take a look? So, if you have a PGF sequence, is it settings in the amplifier that are not behaving, or is it actually the acquisition end that's not doing what you intended to do?
Okay, so I propose, Telly, that you will get in contact with
So
Yes,
maybe
the question later on directly.
maybe I can help here a little bit. I quickly glanced over that question as well. So it looks like those cardiomyocytes, you may not depolarize them far enough or for long enough to have the the voltage exceed the threshold and to elicit an action potential. But it's quite clear for this question we are gonna need more information what specifically the experimenter is doing, and then we will be happy to address that. So we will contact you offline and then make a compilation of this question and the answer, of course, available in that list of question and answers that we're going to publish, as Lars mentioned.
Then I have a question for Jan. Hi, can it, I think it means the iTEV, can it be used in actually isolated neurons?
Acutely isolated neurons would typically be too small. So most neurons that I have worked with, and I believe that goes for virtually all mammalian and also most invertebrate neurons, when you acutely isolate them, they tend to be fairly small, maybe 10 microns in diameter. Some of them are a little bit bigger. But in most cases, too small for two-electrode voltage clamp. That means you would disrupt, you would terminally damage the cell when you try impaling them with two electrodes, and also the currents would likely be too small for you to properly resolve in two electrode voltage clamp recording.
Okay, one more question. Then we're going to finish the webinar because we're already a little late. When one is performing perforated patch clamp and one wants to invoke action potential in cell culture, do you recommend to use a holding potential of minus 70 millivolt before to change to current clamp mode?
Yeah, I would say that depends on the cell type. The question, Lars, remind me, does the question say what cell type that is?
No, it does not. Perforated patch clamp.
Okay, so the holding potential of a cell varies over a fairly wide range. Many insect cells, for example, are relatively far depolarized. They have holding potentials as small as minus 50, minus 40 millivolts in many cases, and can range all the way down to minus 100 millivolts in human cardiomyocytes, for example. So depending on where a healthy cell in physiological conditions, where that membrane potential, resting potential sits, that's what I would recommend to use before switching to current clamp. But then again, it depends on the cell type, and some cells may differ. Again, we may have to ask about more information there, and we will do that offline. So with that, as Lars mentioned, let us finish the webinar. We will keep it running for another 10 minutes or so, so you have a chance to ask further questions. Use the Q&A panel. All you type there will be recorded, and we will get back to you by email then. Your email, since you logged in, your email address is logged as well. We will contact you at that email address. We would all like to thank everybody for being here today. Wish you happy holidays and a happy new year. And we look forward to seeing you at our user meeting at the Biophysics Conference in San Francisco, or at our next webinar, which will take place maybe 2 months after that. So maybe in April timeframe. That's what I would expect. Thank you very much. As we said, we will mute everything, go offline ourselves now, but keep the session open for another 10 minutes or so.